Hello everyone. In today's lecture, we are going to study a very important topic in marine and material engineering, the metallurgy of steel and cast iron. Metallurgy is the study of metals, their structure, properties, and behavior under various conditions. Among all metals, iron and carbon alloys, that is steel and cast iron, are the most widely used materials in shipbuilding and marine engineering because of their strength, availability, and adaptability. Let's begin with pure iron, which is also known as ferrite. Ferrite is soft, ductile, and has considerable strength, but by itself it is not strong enough for engineering use. To make it stronger, we add carbon to the iron. This addition of carbon leads to the formation of different structures which give iron and steel their unique mechanical properties. Formation of iron carbide and perlite. When carbon combines with iron, it forms a compound known as iron carbide or Fa3C, which we call cementite. Cementite is very hard and brittle. In steel, ferrite and cementite appears together in alternating layers, forming a structure known as perlite, named for its mother of pearl appearance. Now, as the carbon content increases, more cementite and perlite forms, and the amount of free ferrite decreases. At around 0.9% carbon, the structure becomes entirely perlite, with no free ferrite remaining. If carbon increases beyond this, free cementite appears, which makes the metal harder but also more brittle. So, by controlling carbon, we control the balance between strength and ductility. Carbon in two states. Carbon can exist in two main states, crystalline state as diamond or graphite, and non-crystalline state as amorphous carbon. This behavior of carbon plays a key role in how iron and steel solidify and behave under heat treatment. Steel and cast iron composition range. The difference between steel and cast iron lies mainly in their carbon content. Steel contains up to 2% carbon. Cast iron begins where steel ends. It contains about 2 to 4% carbon. The form in which carbon appears either as cementite or as graphite depends on the cooling rate and other solidification factors. For example, grey cast iron consists of perlite and graphite and is soft, easily machined, and commonly used in marine engineering. White cast iron contains perlite and cementite, making it very hard and brittle. In marine applications, grey cast iron and malleable iron are preferred, while white cast iron is usually avoided because of its brittleness. The iron carbon diagram. The iron carbon equilibrium diagram is the foundation of steel metallurgy. It shows how microstructures changes with carbon content and temperature. By studying this diagram, we understood how ferrite, perlite, cementite, and austenite form and transform during heating and cooling. This knowledge is essential for understanding heat treatment processes such as annealing, hardening, and tempering. Every marine engineer should be familiar with this diagram because it directly relates to material performance in machinery components. Material properties and their importance. Now let's move to the properties of materials which play a vital role in selecting metals for engineering use. Ductility. Ductility is the ability of a material to be drawn into wire or elongated without breaking. It is measured by the percentage elongation and reduction of area during a tensile test. Brittleness. Brittleness is the lack of ductility. A brittle material fractures suddenly without significant deformation. Malleability. Malleability is the ability of a material to be hammered or rolled into sheets without cracking. It is similar to ductility but occurs under compression instead of tension. Elasticity. Elasticity is the ability of a material to return to its original shape once the applied stress is removed. For example, a spring steel shaft bends under load but regains its shape afterward. Plasticity. Plasticity is the opposite of elasticity. It refers to the property of retaining deformation after the load is removed. Hardness. Hardness is the resistance to wear, abrasion, or erosion. Harder materials resist scratching and indentation. Strength. Strength is the ability to withstand load without failure. It is measured as ultimate tensile strength. Toughness or tenacity. Toughness is the ability to absorb energy and resist shock or variable loading. A tough material combines strength and ductility. It resists impact and does not fracture easily. Other properties. Other important properties include corrosion resistance, essential in marine environment, electrical conductivity needed for electrical systems, thermal conductivity important for heat exchangers and engines. Factors affecting material selection. When selecting a material for any marine component, we must consider the following factors. Working condition. Determine whether the environment is corrosive, erosive, hot, or subject to fatigue and shock. For example, a ship side valve must withstand corrosion, erosion, and impact. Manufacturing method. The method of manufacturing affects material choice, casting, forging, machining, or drying. Complex shapes like valve bodies are usually cast, while shafts are often forged or for strength. Repairability. The ability to weld, braze, or metal lock a component for repair is crucial in shipboard operation. Cost. The chosen material should be should meet technical requirements while staying within an economically acceptable range. Let's understand with an example. The selection of material for a ship side valve. Working condition. The valve operates in a corrosive and erosive environment and may experience minor impact loads and temperature variations. Required properties. The material must have adequate hardness, corrosion resistance, and impact strength. Manufacturing conditions. The valve shape is intricate, so it must be casted rather than forged. Possible material options. Cast iron, inexpensive but brittle, low impact strength. Cast steel, strong and tough but less corrosion resistance. Phosphor bronze, excellent corrosion resistance and toughness but expensive. Conclusion. The choice depends on the balance between cost, repairability, and performance. Generally, we can arrange them in order. Cast iron, first priorities, then cast steel, then phosphor bronze, showing increasing cost, corrosion resistance, and impact strength. Let's summarize our today's discussion. Both steel and cast iron are iron carbon alloys. The key difference lies in carbon content, steel up to 2%, cast iron 2 to 4%. Their microstructure, a mix of ferrite, perlite, and cementite, defines their properties. Grey cast iron, containing graphite, is widely used in marine applications due to its machinability and damping capacity. Material properties such as ductility, toughness, hardness, and corrosion resistance determine their suitability for different purposes. When selecting a material, always consider working condition, manufacturing process, repairability, and cost. Proper selection ensures safety, reliability, and cost efficiency in ship operation. Thank you for listening. In our next lecture, we will discuss one on other topics. Thank you for today.